In this lecture, we're going to go over some additional concepts that relate to Lewis structures. These additional concepts include formal charge and octet rule, which, if you recall, I actually prefer to call the noble gas rule. Exceptions. And I touched on some of these exceptions to the octet rule in the first video, but I'm going to detail them a little bit more carefully in this video after we've gone over formal charge. So let's start with formal charge. I think the name formal charge is very deceptive because the word formal tends to make it sound real, important, official. But formal charge is actually not a real or official or actual charge at all. It is just a measure of how an atom is holding electrons in a molecule compared to as a free atom. A measure of how an atom is holding electrons in a molecule compared to as a free atom. So what we're looking at is how many electrons, and we focus on valence electrons in this because the inner shell electrons generally aren't affected by bonding or forming a molecule or forming an ion. It's the valence electrons that participate. So what we're looking at is how many valence electrons the atom has. And that's unbound before it's part of the molecule. And then we're also looking at how many electrons the atom has in the molecule. So we're comparing this, and any difference between the number of valence electrons the atom has before it's bound and how many electrons it has in the molecule is what gives it a formal charge. So if it has more electrons in the molecule than it did as a free atom, it has a negative formal charge. If it has the same number for both, it has 0 formal charge. If it has fewer electrons in the molecule than it did in the atom, then it has a positive formal charge. When we talk about electrons in the atom as the molecule, we're doing this a little bit differently than when we add up electrons to determine if it has a complete octet. For formal charge, and only for formal charge, bonds only count as 1 electron. So, a single bond. So a single dash would be 1 electron. 2 dashes would be 2 electrons. When we count towards the octet, we count the whole single dash as 2 electrons. But when we're doing formal charge, we want to acknowledge the fact that that bond is actually shared between 2 atoms. So we can only count 1 of those electrons towards formal charge. On the next page, I'm going to go over how we calculate formal charge for some of the molecules that we made in the first video. Before we do that, though, I just want to let you know that a resonance structure with the lowest formal charges is the most stable. So a resonance structure with the lowest formal charges is the most stable. Right, so when I say the lowest formal charges, that's a little bit deceptive. It's what I should say is the smallest magnitude, which means the closest to zero. So in this case, a formal charge of, say, -1 and +1 would be considered higher than 0, or if you're looking at like -3 and +2. -3 is low, but that's actually high because it's further away from 0. So it doesn't matter if it's negative or positive. What we're looking at is the numbers being the closest to 0 or the smallest numbers. Okay, so another thing that we can get from formal charges is that the formal charges of each atom in the molecule will add up to the charge of the molecule. The formal charges of each atom in the molecule add up to the charge of the molecule. Okay, so we might think, well, wait, aren't molecules neutral? So what I'm talking about here is when we would have polyatomic ions. So if we have a polyatomic ion, the formal charges will add up to the charge of that ion. Otherwise, if it's not a polyatomic ion, its charge should be 0 and the formal charges should add up to 0. All right, let's go to the next page and actually do some examples of this. All right, so I'm going to start with a really simple molecule so that we can understand how this works, and then we'll go through some more complex examples. So the molecule I'm going to start with is water, H2O. And we saw in the first video that its resonance structure, or its Lewis structure, looks like this. Okay, so formal charge is equal to the valence electrons minus the associated electrons. That's the equation we're going to use. Associated electrons are all unbound electrons and half of the bonded electrons. So what we're looking at is dots and dashes or lines. So this is a lot easier than all of this makes it sound like. Let's look at an example. Okay, so oxygen, well, let's start with hydrogen because hydrogen's really easy. Both hydrogens in this molecule are the same, so we only need to do this for one. Okay, so hydrogen has one valence electron. In this molecule, it has one dash and 0 dots. So we end up with 1 minus 1, and that gives us a formal charge of 0. Oxygen has 6 valence electrons. In this molecule, it has 2 dashes and 4 dots. That gives it also a formal charge of 0. We end up with 6 minus 6. So none of these atoms are carrying a formal charge. They're all 0. And that would make sense because water is neutral. It's not it's not ion. So the charge of water is 0. The formal charges add up to 0. So essentially, when we are calculating formal charges, what we're just doing is adding up the dashes or the lines and the dots. And we're subtracting it from the valence electrons. And the valence electrons are always in the free atom, the unbound atom. Okay, let's do another one. We're going to do the carbonate ion. Okay, the carbonate ion is CO3 2 minus, and in the last video we found its Lewis structure. Oops, that got a little messy. Let me fix it. So we found its Lewis structure to consist of one single bond or two single bonds to an oxygen and one double bond to an oxygen. And then that whole thing shared that 2- charge. All right, so we actually have two different oxygens here. We have ones that have 3 lone pairs and 1 bond, and we have one that has 2 lone pairs and 2 bonds. So I'm going to call them oxygen A and oxygen B for the sake of calculating their formal charges. All right, so the formal charges, carbon. Carbon has 4 valence electrons. In the molecule, it has 4 dashes and no dots. That gives it a formal charge of 0. Oxygen A oxygen has 6 valence electrons. In the molecule, it has 1 dash and 6 dots. That's going to give it a formal charge of -1. Oxygen B, oxygen still has 6 valence electrons. In the molecule, it has 2 dashes and 4 dots. That gives it a formal charge of 0. So we had two oxygen A's. So we would have to multiply that by 2. 0 plus -1 plus -1 plus 0 gives us a total charge of -2. And that matches the charge on the molecule. This is a good way for you to check your work to make sure you've done your formal charges correctly. If your formal charges aren't adding up to the charge of the molecule, then you've either missed some electrons and you haven't made your Lewis structure right, or you haven't done your formal charges correctly. Okay, we are going to do a little bit of a more complicated one now to sort of explore some different features of formal charges and Lewis structures and what we can do with it. So we are going to do the NCS minus ion. And again, we found the Lewis structure of this in the first video. And it turns out that it's a resonance structure. So it has 3 different possible resonances. It can either have 1 single bond and 1 triple bond, 2 double bonds, or again a single triple combination, but with the bond switching between the ions. So these are the 3 resonance structures of the NCS minus ion. We're going to calculate the formal charges for every atom in every resonance structure. I know it seems like it's going to be tedious, but it's actually not too bad. So we're going to call this one structure 1, this one structure 2, and this one structure 3. 1, 2, and 3 are just totally arbitrary so that I can keep track of it down below. So in structure 1, nitrogen has 5 valence electrons. And in this molecule, it has 1 dash and 6 dots. That gives it a -2 formal charge. Carbon has 4 valence electrons. In the molecule, it has 4 dashes and 0 dots. Formal charge is 0. Sulfur has 6 valence electrons. In the molecule, it has 3 dashes and 2 dots for a +1 formal charge. In the second resonance, we have nitrogen, carbon, sulfur, and the valence electrons come from the atoms, so those never change. We can just go ahead and fill those out if we want to for all 3 resonance structures. Because the valence electrons come from the position on the periodic table, that's constant. It doesn't matter which resonance structure it is. What's going to change is the number of dots and dashes. So in resonance structure 2, nitrogen has 2 dashes and 4 dots, gives it a -1 charge. Carbon still has 4 dashes and no dots. And now sulfur has 2 dashes and 4 dots. Last one, nitrogen has 3 dashes and 2 dots. That gives it 0 formal charge. Carbon, again, 4 and 0, 0. And sulfur now has 1 dash and 6 dots. Oops, that's supposed to be a 6. That gives it a -1 formal charge. So let's take a look at this. I said if you've done it right, your formal charges should add up to the charge of the molecule. So we have -2 plus 0 plus 1. That adds up to -1. This one adds up to -1, and this one adds up to -1. They all add up to -1. That means that we've done everything right. So one of the interesting things we can get from this is which resonance is potentially the most stable. We've already discussed the fact that the one with the lower magnitude, the smaller formal charges, is more stable. That would mean that this first resonance would be the least stable because it has a -2 and a +1. So these are the highest formal charges. The highest formal charges indicate the least stable structure. In the next two scenarios, both the formal charges are the same, -1, 0, 0, 0, 0, -1. However, one of these structures is actually more stable than the other. When it's an option, we want the negative charge on the most electronegative atom. That's going to give us the most stable configuration. So it's most stable if the negative charge is on the most electronegative atom. And so what I'm talking about here, that electronegative atom, electronegativity, that's just that value from the periodic table, that chi value, which is somewhere between like 0.8 and 4.0 is the highest. So the higher electronegativity, the more that atom is able to stabilize a negative charge. So we want the negative charge on the most electronegative atom, or alternatively, positive charge on the least negative atom. So that's going to give us the most stable resonance structure. So if we come back up and look at our two options here, structure 2 or structure 3, structure 2 puts the negative charge on nitrogen, and structure 3 puts the negative charge on sulfur. Sulfur's electronegativity is 2.5 and nitrogen's electronegativity is 3.0. So structure number 2 puts the negative charge on the most electronegative atom. That would make it the most stable of the 3 resonance structures. Most stable because the negative charge is on the most electronegative atom. So what this means to us is that all three of these resonance structures are going to exist. The structure will go back and forth between all of these, but we'll spend the most time in structure number 2 because that's the most stable, and the least time in structure number 1 because that's the least stable. Okay, so now that we've covered formal charges, we're going to go back and talk about exceptions to the octet rule that we can expand upon now that we've learned about formal charge. There are 3 octet rule exceptions. The first one is less than 8 electrons, or an incomplete octet. This is possible for atoms that are in n equals 2, the second row of the periodic table. In order to get 8 electrons, they would be like neon, but that's adding a lot of electrons onto them. So they tend to be stable with less than 8 electrons. So the 3 elements you're going to see this for are beryllium, boron, and aluminum. These can be stable with less than 8 electrons. What that means is that when you make a Lewis structure, you don't necessarily have to have 8 electrons on there. So you might not need to make double bonds. An example of a molecule that does this is BeH2. The skeletal structure for BeH2 is a single bond each hydrogen. Beryllium has 2 valence electrons. Each hydrogen has 1 electron. That gives us a total of 4 electrons to work with. So we've used those 4 electrons up to make the single bond, and we don't have any electrons left. Hydrogen is fine. It has a complete octet for it because hydrogen's octet is only 2 electrons. Beryllium, however, only has 4 electrons. In theory, it could hold up to 8 and be like neon, but beryllium is one of these things that's stable that way. So that's it. This is just what the molecule is, and it's stable as it is. So what you need to be on the lookout for is if you have beryllium, boron, or aluminum compounds, it may be okay for the beryllium, the boron, or the aluminum in the center to have less than 8 electrons. The next exception to the octet rule is when we have more than 8 electrons. This is called an expanded octet. This is possible for any atom in row 3 of the periodic table or lower. Possible for any atom in n equals 3, row 3 of the periodic table or lower. The reason this is possible is that these elements have empty d orbitals, so they have a spot to put more than 8 electrons. At this point in time, I don't think it matters if you know or remember that it's possible because of the empty d orbitals. You really just have to remember that if the atom is in n equals 3 or lower on the periodic table, it's okay for it to have more than 8 electrons. So let's look at a couple examples of these. One of the things we did in video 1 was XeF2. Its Lewis structure looked like this. And we can do formal charges on this. So let's calculate some formal charges. Fluorine has 7 valence electrons, and in the molecule it has 6 dots and 1 dash. That gives it a formal charge of 0. The other fluorine is the exact same way. Its formal charge is going to be 0. Xenon has 8 valence electrons. In the molecule, it has 6 dots and 2 dashes, so its formal charge is 0. So even though it has an expanded octet, with xenon holding 2, 4, 6, 8, 10 electrons, it still has a formal charge of 0, and xenon is in the 5th row of the periodic table, so it can have an expanded octet. We can also go back up to BeH2 and do its formal charges, right? So hydrogen has 1 valence electron minus 1 dash, no dots. So it has 0 formal charge, same for the other hydrogen. Beryllium has 2 valence electrons and 2 dashes, no dots. It also has a formal charge of 0. So that can help you see why this structure is stable even with an incomplete octet. If we had to add extra electrons or extra bonds to beryllium, it would have a negative formal charge, and that's not as stable as a 0 formal charge. So formal charges can also kind of help us explain why structures are stable when they don't meet the octet rule. All right, let's do one more example of an expanded octet, and this time we're going to do it for something where the formal charges can help us determine what resonance structures might be more feasible or more stable. And this would be something that we wouldn't pick up on with the octet rule alone. So we're going to do this for so we're going to do this for the polyatomic ion SO4 2-. The Lewis structure for SO4 2-, the skeletal structure will be sulfur in the middle with 4 single bonds to oxygens. Sulfur has 6 electrons. Oxygen also has 6 valence electrons, and we have 4 of them, so that gives us 24 electrons coming from oxygen. And then the charge is 2-, so that's going to give us 2 additional electrons to work with. So we have 32 electrons to distribute in this structure, and we have used 8, making our 4 single bonds. That takes us to 26 electrons left. Or if I could math, 24 electrons left. All right, so we have 24 electrons left. Each oxygen needs 6 more electrons to fulfill its octet. So we'll start putting lone pairs around those oxygens. And that's going to use up 24 electrons. So we don't have any electrons left. All right, so this would be the Lewis structure. It has a negative charge. Everything has a complete octet. Every oxygen has 3 lone pairs for 6, plus a single bond for 2 more, so 8. And sulfur has 8 single bonds, or 4 single bonds for 8 electrons. So everything's octet is filled. Let's do the formal charges here. Okay, so sulfur has 6 valence electrons. In the molecule, it has 4 dashes and no dots. That's going to give it a formal charge of +2. All the oxygens are the same, so I only have to do this once. Oxygen has 6 valence electrons. In the molecule, it has 1 dash and 6 dots for a -1 charge. So there would be 4 of these. So if I was going to add this up, that would be -4 plus 2 gives me -2, which matches the charge on the ion. And I'm sorry, this should have been a -2 out here too. So while this fulfills the octet rule, it leaves us with fairly high formal charges. +2 is a fairly high formal charge. So what we're seeing here is that sulfur would like to have more electrons because it has a formal charge that's positive, and oxygen would like to have fewer electrons because it has a formal charge that's negative. So we can unload some of the electrons from sulfur, or oxygen rather, into a double bond with sulfur. And that makes those electrons shared between the sulfur and oxygen instead of just on the oxygen. If we do that to one of them, that will decrease the formal charge of sulfur by 1. If we do it to 2 of them, that will decrease the formal charge of sulfur by 2, which will take it to 0, which is what we want. So the resonance structure where sulfur has 2 double bonds to oxygen and 2 single bonds to oxygen is going to be a more stable resonance structure than the one before it, than the one we drew first, even though this one actually disobeys the octet rule, right? So in this structure, sulfur feels like it has 2, 4, 6, 8, 10, 12 electrons. That's an expanded octet. That's okay. Sulfur is in the third row of the periodic table, so it can hold more. And in this structure, we've now been able to minimize the formal charges. So we can do those just to prove it to us. There's 2 types of oxygens. I'm going to call them A and B. This one's also a B and this one's also an A, so we only need to do them once. So sulfur, oxygen A, and oxygen B. Sulfur is now 6 valence electrons minus 1, 2, 3, 4, 5, 6 dashes and no dots. Oxygen A is 6 valence electrons minus 2 dashes and 4 dots, so 0. And oxygen B is 6 minus 6 dots and 1 dash is -1. So there's 2 of each oxygen. That's going to give us a total of -2 for all the formal charges added up. Just to verify that our formal charges add up to the charge of the molecule. Okay, so both of these resonance structures are possibilities, but this one is much more stable because it has lower formal charges. If we hadn't done formal charges, if we hadn't learned about that, there would have been no reason to think to even make this structure, because the first structure we drew totally completes the octet rule, which is what we sort of learned about. So at first glance, we might think this first structure is the stable, better one, but once we account for formal charges, we see that this second one is more stable. I only drew one of the possible resonances here for simplicity, but the reality is that those 2 double bonds could alternate between any of those oxygens. So there's multiple variations of this particular resonance. Okay, so there is a third exception to the octet rule, and that's going to be for something called free radicals. Have you ever heard of a free radical? It's one of those terms you hear in advertising, some things like it helps take care of free radicals. Green tea is good for you because it helps eliminate free radicals, and you should wear sunscreen because it helps prevent free radicals. Free radicals are simply molecules where you have a single electron instead of a lone pair. Free radicals are not stable molecules. They're really reactive. And so that's why we look to remove them from our system if we have free radicals. From a chemical standpoint, free radicals are interesting because of their reactivity, but they don't stick around for long. They're unstable, they're reactive, so there's not a whole lot of examples of free radicals. When we deal with a free radical, We just use that single electron in place of a pair of electrons in terms of making the Lewis structure, calculating formal charge, etc. All right, so let's do an example of a molecule that has a free radical. NO2 is an example of something that does. Nitrogen has 5 electrons, oxygen has 6 electrons, and there's 2 of them. So that gives me a total of 17 electrons to make my Lewis structure with. Nitrogen has lower electronegativity. It's going to be in the center with 2 single bonds that use up 4 electrons and leave us with 13 electrons. Oxygens each need 6 more electrons to complete their octet, right? We always do the outer atoms first. That used up 12 electrons, which leaves us with 1 electron left. So what do we do at this step? Well, we put whatever electrons are remaining on the center atom. We only have 1 electron, so we put 1 electron there. So see, this is where we get that single electron instead of the lone pair. Whenever your when you total all your available electrons up and you get an odd number here, that's going to be a sign that you're going to have a free radical, because whenever you have an odd number, you're going to end up with the situation where you have 1 electron, which it's not enough to make a bond out of. So you just end up with this 1 electron instead of a pair of electrons on one of your atoms. So if we think about this from the octet rule standpoint, both oxygens have a complete octet. Nitrogen does not, right? So nitrogen here only has 1, 2, 3, 4, 5 electrons. So we're going to need to make a double bond. If we do that, that's going to give it 2 more electrons, so 7. If we tried to make another double bond, that would give it 9 electrons, which is impossible. We cannot have an expanded octet for nitrogen because it's not below the 3rd row of the periodic table. So in this resonance structure, nitrogen is going to have to be short of the octet rule. So we're going to have 2 options. The single bond can be on this side or this oxygen, or the single bond can be on the other oxygen. So these resonance structures are, essentially the same. It just has the double bond rotating back and forth. So working with free radicals is a little bit weird because we're just so used to pairing up electrons, but we can have a situation where we don't have that pair of electrons. What this would really mean is that even in the molecule, we have an orbital that has 1 electron in it instead of 2 electrons. This happens most commonly, the most common place you're going to see free radicals is for nitrogen compounds. And that's not to say all nitrogen compounds are free radicals, but that's going to be the most common free radical. Okay, so this wraps up all the topics that have to do with Lewis structures. I'm going to post one more video that'll be really short on Chapter 8 concepts, but at this point in time, you should be able to complete the Lewis structure worksheet. So at the end of the first video, I told you to try the first 3 columns. Now that you've watched the second video, you should be able to do the 4th column, which is the formal charges one. At this point in time, you should also be able to complete the Chapter 8 study and problem set. So I'd recommend that you work on both of those to check your comprehension and practice with the techniques that were in this video as well as the first Lewis structure video.